Alright, let's take a look at transformations. So I'm just going to kind of summarize how to perform transformations, the different types of transformations, how to change one graph to the other, as well as this notion of mapping notation, which is really useful in looking at transformations. Right? Now, in this sense, there's basically, for transformations, I like to look at transformations as two types. Okay, so transformations can be grouped as modifications, and modifications will change the shape of the function. And there's also translations. Translations change the position of the function. Okay, so I like to think about modifications as two main branches: stretches, shrinks. Right? You can also call stretches expansions. You can also call shrinks compressions. Right? And there's another group of modifications, right, which are called reflections. Okay. And all of these transformations will have to do with x or y values, right? So we can have stretches or expansions on the vertical, which is the y values, or the horizontal, which is the x values. Right? It's the same idea with shrinks and compressions. We can have vertical shrinks, right? Or we can have horizontal shrinks or compressions. Okay, and translations, we can also affect them on the vertical and the horizontal. Now for reflections, right, a vertical reflection, I'm going to just kind of show you guys really quickly what a vertical reflection is. Right, so like if this a vertical reflection, if you have a graph, and let's call this guy f of x, a vertical reflection is a reflection over the x-axis or in the x-axis, and you're going to basically have a graph that looks like this. This is negative f of x. Okay, so you can notice here that we have the same x values, but we have opposing y values. Okay, so like if we're looking at this value, this is x and this is y, right, this is going to be x and negative y. So this is what we call a vertical reflection. Now a horizontal reflection is going to look kind of like this. Okay, so in this case, instead of x, we have negative x. Okay, so green, we have a horizontal reflection. This is going to look like f of negative x. Okay, so these are just some examples of transformations, but what we're responsible for, and you probably have looked at this in previous grades. If you want, you should review some of the videos that I have about transformations, what they are, if you need a much more detailed refresher. But what we need to look at right now is a functional method of demonstrating transformation. So we want to look at transformations, g of x as a transform function, f of x as a parent function. So we're transforming f of x into g of x. Okay, it doesn't matter what functions you use to be the parent and the transform function. Okay, but we're going to look at this template as g of x is equal to a f of k x minus d plus c. Okay. And you might see this using different variables. These are just the variables that I've chosen to use, and I'm kind of correlating it with this excerpt I got from a textbook. Okay, so in this case, a here is your vertical stretch or shrink factor, and all of this is kind of mentioned in this excerpt, right? K here, well, 1 over k is your horizontal stretch or shrink factor. D here is for the horizontal shift. C here is the vertical shift. Okay, and you can kind of correlate this with some of the terminology that's found in this portion, right? Looking at A, if A is greater than 1, then in the graph y is equal to f of x is stretched vertically by factor of A. Factors means that we multiply whatever the x or the y value is by that value or that factor. Because A is a vertical stretch or shrink factor, it's going to multiply the y values. Now, when A is a fraction, when it's greater than 0 and less than 1, the graph is compressed vertically by factor of A. When A is less than 0, the graph is also reflected in the x-axis, okay? The value of K determines whether there is a horizontal stretch or compression, right? So when K is greater than 1, the graph is compressed horizontally by a factor of 1 over K. So compressed horizontally means that we're basically shrinking it horizontally, right? So if you're shrinking it horizontally, the shape of the curve will get longer, narrower. And when K is a fraction, the graph is stretched horizontally by 1 over K. Okay, and when K is less than 0, the graph is also reflected in the y-axis. Okay, so for values of D and C, D is your horizontal shift. So if D is greater than 0, right, we have a shift D units to the right. D is less than 0, we have a shift D units to the left. Conversely, for C, this is a vertical shift. So if C is greater than 0, then the graph is shifted C units up. And if C is less than 0, the graph is shifted C units down. Okay? So using this notion, we can think about all of our transformations for g of x as transformations from f of x. So actually, before we look at g of x, if we consider points f of x, if f of x has the points x and y, then g of x is going to be some kind of transformation to x and y, right? So if we're looking at transformation of f of x into g of x, right, we can look at this template where for the y values we can have a vertical stretch, so a times y values, a vertical shift, c units up or down, so I'm going to use plus c. For the horizontal values we can have a horizontal shrink or stretch, and it's always by factor 1 over k, so I'm going to write 1 over k here, and this is going to be either a shift d units to right or left, so I'm going to do plus d here. Okay, so this is basically what we call mapping notation. The mapping notation creates a transforming equation. Okay, so the mapping notation creates a transforming equation where we can change our original values of our parent function into our transform points on our transform function. Okay, so I'm going to show you guys examples of that, right? But make sure you can keep this little excerpt here. It has all of the rules that you basically will need to kind of work through these transformations. All right, let's describe the transformations that must be applied to y is equal to x squared to obtain the function f of x is equal to negative x plus 3 squared minus 5. Okay, so we want to start with our function y is equal to x squared. This is a parent function and it's a quadratic function, right? And we want to look at its transform function. Y is equal to a, b, whoops, let's use k here, k x minus d squared plus c. Okay, so this time we're just looking at the function, and we're basically going from x squared into this guy. Okay, so by looking at that, you can notice here that f of x is equal to negative x plus 3 squared minus 5. A here is equal to negative 1. Okay, b here is 1, so we don't have to worry about b. The d value here is actually negative 3. Okay, because the negative 3 would make it positive 3, right? You don't need to put brackets around it. Okay, so it should be negative 3. And the c value, the vertical shift here, is going to be negative 5. Okay, so we're going to look at all of our transformations. So the first transformation you can see, if a is less than 0, we have a vertical reflection. And a vertical reflection is basically a reflection in the x-axis or over the x-axis. Okay, and in this case, what we mean by vertical reflection is y is equal to negative x squared. Okay, so what does that have to do with the function? So how does that affect the function, right? Now we have this question that's telling us to graph the function. Instead of graphing the function, guys, what I'm gonna do here is I'm going to show you this using a table of values, because when you graph multiple transformations, it makes it really messy. I'm gonna start with x and y is equal to x squared. I'm gonna take these points, so -2, -1, 0, 1, and 2, and these are the equivalent y values. Okay. In a vertical reflection, what's going to happen here is that all of the y values will become negatives. Your x values won't change. So vertical transformations will not change the x values, right? So in this case, I'm going to copy down my x values from the previous transformation, from my previous parent function, and now we're going to have basically negative y, or basically y is equal to negative x squared. Okay, so you're going to see -4, -1, right? 0, -1, and -4. Okay, so that's what happens to our points when we apply this transformation. Now, in our second scenario, okay, we have a shift. Okay, so we have a horizontal shift 3 units left. Okay, so if we have a horizontal shift 3 units left, look what happens to our point. So because it's a horizontal shift, we're only going to be affecting our x values and not our y values. So I'm going to copy down the y values from the previous step. You can notice here that the function now will look like this. Y is equal to negative x plus 3 squared. Okay, and what we're going to do here is we're going to subtract 3 to all of our x values. So we're going to get -2 minus 3, which is -5, -1 minus 3, which is -4, 0 minus 3, which is -3, 1 minus 3 is -2, and 2 minus 3 is -1. Okay, so these are our points. In the last case, we have a third transformation. We have a vertical shift 5 units down. Okay, so if we have a vertical shift 5 units down, what that's going to do to our function, now we're going to have y is equal to negative x plus 3 squared minus 5. And if you address the points here, whoops, let me just make some space here. Okay, so if we address the points, right, because we have a vertical shift, you can copy down your x values. It should basically be the same x values as the previous transformation, so -2, -1. For y values, what I'm going to do here is I'm going to subtract 5 from each of these y values. So -4 minus 5 is -9, -1 minus 5 is -6, 0 minus 5 is -5, -1 minus 5 is -6, and -4 minus 5 is -9. Okay, so this is what your final points will look like. Okay, so we can actually graph all of these points and create our graphs for each transformation. I just thought we would look at it using a table of values because it's a lot more organized and more effective in observing what happens to these transform points. Alright, let's take a look at another transformation question. So the point 1,8 is on the graph of y is equal to f of x. Find the corresponding coordinates of this point on each of the following graphs. In the graph that we're given here, y is equal to 0.5 f of 0.5 x plus 3 plus 3. Okay. So in this case, what we want to do first is identify all the transformations, and let's do that in words. And then in the next case, we need to use all those transformations and create a transformation equation, right, or transforming equation. And this whole process here is mapping notation, right? So let's look at a template of the transform function. Y is equal to a f of k x minus d plus c. We know that a is the vertical modification factor, 1 over k is the horizontal modification factor, D is the horizontal shift, C is the vertical shift, A here is 0.5 or 1/2, K here is 0.5, so 1 over K, which is 1/2, so 1 over K is 2. Okay, so this is the value that we should be looking at. This is the value of A that we should be looking at. D here is -3 and C here is +3. Okay, so the first transformation in words is that there is a vertical compression by a factor of 1/2. So there's a vertical compression by a factor of 1/2, or you can write this as 1/2 f of x. In the second transformation, we're looking at this k value, or specifically we're looking at 1 over k, and there is a horizontal expansion or horizontal stretch by a factor of 2, and in function notation we can write this out as 1/2 f of 1/2 x. In the third transformation, we have a horizontal shift 3 units left. So we have a horizontal shift 3 units left. So how we'd write that, 1/2 f of 1/2 x plus 3. So we can see that we're building the function piece by piece by its transformations, its component transformations. In the fourth transformation, we have a vertical shift 3 units up. So we have vertical shift 3 units up, so the way we would write this is 1/2 f of 1/2 x plus 3 plus 3. Okay, so now that we have a collection of all of our transformations, we want to translate this into mapping notation. I want to create a transform equation. So this is x, this is y, these are the original points of our function or our parent function f of x. And if we look at all the transformations we did to our y values or our vertical axis, we had a vertical compression by a factor of 1/2. So we had 1/2 times y. We also had a vertical shift 3 units up, so 1/2 y plus 3. We also had, so those are basically all of the vertical transformations. Let's take a look at some of the horizontal transformations. We had a horizontal stretch by a factor of 2, so you're going to multiply the y value, the x value, by 2, and we had a horizontal shift 3 units left. So you can notice here that I'm just kind of using the modification rules that have to be applied first, and then you do your shifts. Horizontal shift 3 units left, so -3. Okay, so this is your transformation equation. So this is your transforming equation, and this is the whole process of mapping notation. So this is your transforming, let's call it equation. Okay, so now what we need to do here is we need to plug in this point 1 and 8 into the transforming equation. So for x, I'm going to plug in 1. For y, I'm going to plug in 8. Basically, you get 2 minus 3 and 4 plus 3, which is -1 and 7. Okay, so this is your point, your final point on your transformed equation. Okay, so you can do this very straightforward by just kind of by creating the transforming equation and plugging in the original point. Alright, the point 3, 6 is on the graph of y is equal to 2f x plus 1 minus 4. Find the original point on the graph y is equal to f of x. Okay, so this time we're actually working backwards, right? So this time we're given the transformed function 2f, y is equal to 2f x plus 1 minus 4, and we have a point 3 and 6, and we want to go backwards and return to its parent function. Okay, so let's look at all of the transformations we did to our parent function to get to this point. All right, so if we're looking at all those transformations, I'm going to investigate this function really quickly, and we can notice here, and we want to think about this function y is equal to a f of k x minus d plus c. So you want to look at it in this template. So if we are looking at it in this template, you can notice that a here is equal to 2, so this implies there's a vertical stretch. D here is equal to -1, so this is a horizontal shift 1 unit to the right. and c here is -4, so it's a vertical shift 4 units down, right? So I'm just going to write down the transformations in words. So there's vertical stretch by a factor of 2, okay? So there's a vertical stretch by a factor of 2, or you can write it like 2f of x. Second transformation, there is a horizontal shift 1 unit left, or you can write this as 2f of x plus 1. And the third transformation, we have a vertical shift 4 units down. Okay, so that looks like 2f of x plus 1 minus 4. Okay, and in this case, if we do create a transforming equation, so let's do it over here. If we do create a transforming equation, I'm going to look at all the transformations I did to my original function on x and y to get to my transform function. So you have a vertical stretch by a factor of 2, so I multiplied all my y values by 2. There's a horizontal shift 1 unit left, so I subtracted 1 to my x values, and there is a vertical shift 4 units down, so I subtracted 4 to my y values. Now that I have this, we know that we have a point 3 and 6, so this point should be equal to 3 and 6, so x minus 1 is equal to 3, and 2y minus 4 is equal to 6, and you can solve for each of them. So x minus 1 is equal to 3, so x is equal to, I'm going to move the -1 to the other side, 3 plus 1, x is equal to 4. Okay, and if I'm solving for y, 2y is equal to, I'm going to move the 4 to the other side, 6 plus 4, 2y is equal to 10. If I divide this by 2 and this by 2, y is equal to 5. Okay, so therefore the original point is going to be 4 and 5 on the function f of x. Alright, the point 2, 3 is on the graph of y is equal to f of x. Determine the corresponding coordinates of this point on the graph of y is equal to -2 f of 2x plus 5 minus 4. Okay, so what we want to do here is we want to assess all of the transformations that occur to f of x to get us to this transform function of y. And then what we want to do here is, so after we do the assessment of transformations, and we should do this in words, then what we want to do is create a transforming equation. So this process here is called mapping notation. So what I'm going to do here first is I'm going to write down all the transformations. Now we want to think about the transform function. Y is equal to a f of b x minus d plus c. Okay. Now we need to consider the a, the b values, instead of using b I can use k, but it doesn't really matter what the template, whatever variables you use, right? So different schools will teach different variables, right? A is your vertical modification factor, 1 over k is your horizontal modification factor, right? And d is your horizontal shift, and c is your vertical shift. Okay, so a here is equal to -2. K here is equal to 2, so 1 over k here is equal to 1/2. D here is equal to -5, and C here is equal to -4. So having said that, the first transformation I'm going to look at, and you always want to do your vertical and horizontal modifications, which includes reflections first, and then you want to do your shifts. All right, so the first transformation here is a vertical reflection. Okay, so vertical reflection or reflection over the x-axis. Okay, so it's a reflection over the x-axis. And in the second case, so after we've looked at the negative, right? Oh, and this vertical reflection should look like, and if you're looking at this as a function standpoint, it's -f of x. In the second case, we have this 2 value here, and this implies, because the a value is greater than 1, this implies we have a vertical stretch, right, by a factor of 2, right? So we have a vertical stretch by a factor of 2, and this is equal to -2f of x. Okay, so that's just in function notation. So we're slowly building we're slowly piecing together this transform function from our general function. Now the third transformation, okay, so in our third transformation, this should be a 3. In our third transformation, we have this k value, and we know that the k value is 1 over k, so this implies that we have a horizontal compression by a factor of 1/2. So we have a horizontal compression by a factor of 1/2, right? And what this looks like in function notation is negative 2f of 2x, right? So in function notation, we're just kind of building the function together, but in that case, the transformation is still a compression of 1/2, right? So it might look different in function notation in comparison to the actual transformation. In the fourth scenario, we have this d value, and we have a horizontal shift 5 units left. Okay, so this horizontal shift 5 units left, this implies that the reason we have a horizontal shift 5 units left, I think most of the times you guys would have learned this as they take the opposite sign on the inside of the bracket. And this is mainly because of the fact that the format is actually x minus d. So if d is equal to negative 5, then x minus d is x minus negative 5, which is x plus 5. So that's why the sign actually looks inverted. So that's the horizontal shift 5 units left. And the last transformation we have is the vertical shift 4 units down, right? And what this looks like, oh, forgot to write the previous transformation, but the horizontal shift 5 units left is 2 f of 2x plus 5. Okay, in this case we're doing horizontal shift 4 units down, which is negative 2 f of 2x plus 5 minus 4. Okay, so those are all of our transformations. Now what we want to do is we want to create a transforming equation. So a transforming equation, which is this is really the process of mapping notation. A transforming equation is basically what kind of transformations do we apply to x and y of the original function to get to our transform function. So what I'm going to look at first is the horizontal transformations. So I have a horizontal compression by a factor of 1/2, so I multiplied my x values by a half. There's a horizontal shift 5 units left, so I subtracted 5 to the x values. There's a vertical, so now after I've looked at my horizontal, then I look at my vertical transformations. So on the vertical axis, or on the y values, I had vertical reflection, so that's negative y. Vertical stretch by a factor of 2, so negative 2y. And a vertical shift 4 units down, so negative 2y minus 4. Okay, so this guy here is our transforming equation. What you want to do with your transforming equation is you want to take an original point on the parent function and you want to plug it in to find a point on its equivalent point on the transform function. So the way you're going to do this, I'm going to substitute the original point 2 and 3 into this transform function. So for the transformed x value, the new x value, you have 1/2 times 2 minus 5 and negative 2 times 3 minus 4, right? In this case, we basically got 1/2 times 2 is 1 minus 5, so this is negative 4, and negative 6 minus 4 is negative 10. Okay, so this is your equivalent point on your transform function. Alright, let's describe all transformations to the function f of x in words and in mapping notation. Okay, so if we're looking at writing all the transformations in words, we will always have to be doing our vertical and horizontal modifications, which includes vertical stretches, shrinks, reflections, and horizontal stretches, shrinks, reflections, and then we'll do our translations, or horizontal and vertical translations. I like to think about it from left to right, right? I would go this way. So the first transformation here, I can notice here that the a value, and you want to always think about the template as y is equal to a f of k x minus d plus c. Okay, and you can notice here that the first transformation here is referring to our a value, which is a vertical stretch or shrink factor, right? So a here is 1/2, k here is 1/4, right? So 1 over k, which is the factor for the horizontal stretches and shrinks, is 4, right? D here is 5, and C here is 6. Okay, so I'm going to use these values to write down my transformation. So the first transformation I can see here, there's a vertical compression or shrink. Or you can use compression as well, it's the same thing, by a factor of 1/2. Okay, so in terms of function notation, what that really basically means is that we have 1/2 f of x. Okay, so this is the function notation writing it. Our second transformation, we have a horizontal, because 1 over k here is 4, we have a horizontal expansion or stretch by a factor of 4. Okay, so we can write that here as 1/2 f of 1/4 x. Okay, so this builds our function piece by piece. Our third transformation here is basically a horizontal shift five units to the right. So if we have a horizontal shift 5 units to the right, we can write this guy here as 1/2 f of 1/4 x minus 5. Our fourth transformation here is a vertical shift six units up. Okay, so if we have vertical shift 6 units up, then basically we're going to have the equation 1/2 f of 1/4 x minus 5 plus 6. So this is basically what our transformed function looks like, right? So I can just show you guys what it means piece by piece. Now, using mapping notation, I want to look at all the transformations I did to x and y. So the transformations I did to x, I had a horizontal stretch by a factor of 4. So I multiplied all my x values by 4. I had a horizontal shift 5 units right, so I added 5 to my x values. For my y values, I had a vertical shrink by a factor of 1/2, so 1/2 y. And I have a vertical shift 6 units up, so I added 6 to y. Okay, so this is what our mapping notation will look like, right? This is what the transforming equation is. And we can use this to change our points x and y in our function f to our function g of x, which is a transform function.